Next up, we want to find roots of complex numbers, and here's what we know. Every complex number has n nth roots, which means that every complex number has 2 square roots, 3 cube roots, 4 fourth roots, so on and so forth. So what I want to do here is look at the 3 cube roots of the number 8. Well, I already know one of those, and that's the number 2. 2 is the real cube root of 8, so let's look at its graph. The graph of 2 will be the vector that goes from the origin out to the point 2, 0. So here's the graph of one of the cube roots of 8, which is 2. This is what else I know about the cube roots. They distribute themselves evenly around the coordinate plane. So I want 3 cube roots of 8. That means that those 3 cube roots are going to divide the coordinate plane up into 3 equal pieces. So I'm going to have one up here at 120 degrees, and then I'm going to have another one down here at 240 degrees. So 120, 240, 360. So that divides the coordinate plane up into 3 equal parts right there. Each of these complex numbers will have a length of 2. And so there's a picture of the 3 cube roots of the number 8. So now what I want to do is, using this picture right here, write them out in trigonometric form and then convert from that to standard form. So let's just look at my first one here. It's 2, which is 2 cosine 0 plus I sine 0. Well, that turns out to be 2 times cosine 0 is 1, sine 0 is 0, so I just end up with 2. I already knew that, but I wanted to go through the process of writing it in trigonometric form, changing it to standard form. Okay, let's look at this complex number right here. It's 2 times cosine 120 plus I sine 120. So I can see that the reference angle there for that, 120, is going to be 60 degrees. So now I'll convert to standard form. This is 2 times cosine 120 is the same as cosine of 60, which is 1/2, except it's negative because I'm in quadrant number 2. So 1/2 plus I times the sine of 120 is square root 3 over 2. I multiply by 2, and I end up with negative 1 plus I square root 3. So there is my second cube root of 8. Here's my first cube root of 8. And now let's find my third one, which will be 2 cosine of 240 plus I sine 240. So that will be 2 times, okay, cosine of 240 is negative 1/2, plus I times the sine of 240 is negative square root 3 over 2. Now I multiply 2 times this, I get negative 1. 2 times this, I get negative I square root 3. So here is my third cube root of 8. So if I take any one of these cube roots right here and cube it, I end up with the number 8. Now let me just show you that you already knew how to solve this problem previously using algebra. So I want to just continue right here and do the same problem with algebra. If I'm looking for the cube roots of 8, I'm looking for values of x for which x cubed equals 8. I write this in standard form as x cubed minus 8 equals 0. It's a cubic equation which I can factor, x minus 2 times x squared plus 2x plus 4. If I set this factor equal to 0, I get x equal 2. When I set this factor equal to 0, I get x equal, I'll have to use the quadratic formula, negative 2 plus or minus the square root of b squared minus 4 times a times c, all divided by 2 times a. Now I'll simplify this. Negative 2 plus or minus square root of 4 subtract 16, square root of negative 12, all divided by 2. So I have negative 2 plus or minus, when I simplify square root negative 12, I get 2i square root 3, all divided by 2. Now, notice when I take this last expression right here and divide the numerator and denominator by 2, I'll have negative 1 plus or minus I square root 3. When I use the plus sign, I get this solution right here, and when I use the minus sign, I get this solution right here. So my work that I get by solving this problem using algebra corresponds exactly to the work I get when I use my information on complex numbers in trigonometric form and how their graphs are evenly distributed around the coordinate plane to find the three cube roots of 8. So pretty simple problem, and a kind of an interesting fact about complex numbers that they have 3 cube roots. Every one of them does. 4 fourth roots, 5 fifth roots. Let's try one more problem. This time I want to find the 4 fourth roots of this complex number right here. And this time, instead of using the graph, I'm going to use the formula that's in the book. So the 4 fourth roots will look like this. They will be the 4th root of 16. So I take the 4th root of this number, and then I multiply that by cosine of, okay, I'm going to take my angle, 120 degrees, and I'm going to add on multiples of 360, because that's what the period is for cosine and sine, and then I'm going to divide that by 4. So 120 degrees plus 360 times k divided by 4, because I want 4 fourth roots, plus I times the sine of the same thing, my original angle, plus multiples of the period, all divided by 4. And then I'm going to do this for k equal, that's this k, 0, 1, 2, 3. And so as I substitute these 4 numbers in for k, I'll get out my 4 fourth roots right here. So, but before I do that, let's just simplify this a little bit. I end up here with the 4th root of 16, that's the real 4th root of 16, which is 2, times the cosine of, okay, 120 plus 360 divided by 4 is going to be equal to 30 degrees plus 90 degrees times k. Because 4 divides into 120 30 times, and 4 divides into 360 90 times. Plus I times the sine of the same thing, 30 degrees plus 90 degrees times k. Okay, so I write this out right here. This is the formula. Looks pretty complicated when you see it in the book, but it's really just this simple. You take the angle and add on multiples of the period, and then you divide by the number of roots you want, in this case 4 fourth roots. Okay, so I simplify that a little bit. Now I'm going to substitute in k equals 0, then k equal 1, then k equal 2, and then k equal 3, and from that I'll get out my 4 fourth roots. So when I substitute in k equals 0, that's going to give me my first root, which I call w sub 0. So that will be 2 times cosine of, when I put in 0 here, I'll get 90 times 0, which is 0, plus 30, which is 30. Okay, so that's my first 4th root. My next one, which I'll call w sub 1, that'll be what I get when I put in 1 for k, so that'll be 2 times cosine of. 1 times 90 is 90, plus 30 is going to be 110, plus I times sine of 120. Thank you. Did I say 110? No, 120. Okay, so 1 times 90 is 90, plus 30 is 120. So I get 2 cosine 120 plus I sine 120. My second one, or my third one I should say, will be what I get when I let k be equal to 2. Cosine of 2 times 90 is 180, plus 30 is going to be 210. And then my last one, which will be w sub 3, is what I get when I put in k equals 3. 3 times 90 degrees is going to be 270, plus 30 will be 300 degrees. So 2 times cosine of 300 plus I sine 300. Now we could easily graph these 4 roots of the complex number, of this complex number right here, and you would see that they would be evenly distributed around the coordinate plane, and each would be a vector of length 2. So this formula might look kind of complicated in the book, but in actuality it's really pretty easy to use, and this is a look at finding roots of complex numbers.